I'm yet another engineer from MBIOTA, Tim McGilchrist, and today we're going to do a crash course in OCaml modules. I'm sort of assuming that most people don't know OCaml, so that's sort of the basis for the whole talk. So yeah, what to expect from the talk. So we're going to do a little bit about OCaml, but probably not too much into detail about everything in OCaml. It's mostly going to focus on these concepts around modules. And defining what modules are, how we use them, and then we're going to go into a comparison with how modules compare to type classes in Haskell. And there's going to be lots of code, but hopefully it'll be quite understandable code. It's not too dissimilar to Haskell. So as outcomes from this talk, I'd like people to understand OCaml and the module system, and appreciate the difference between modules and type classes. The ML module system or OCaml module system comes up a lot with Haskell, like talking around Haskell needing its own module system and why can't we have a module system in Haskell, and just what that module system would do for us in Haskell. So rather than having sort of people hand waving and going, oh, they can do this, type classes can do that, let's sort of actually look at it and understand what the two things offer. And then perhaps write some OCaml because it's awesome. But first, a bit of an anecdote about why I learned OCaml. About 4 or 5 years, or probably about 3 or 4 years ago, I sort of was looking at a new language to learn. Everyone was doing Haskell because that was cool. So I went, stuff that, I'm going to do OCaml because no one else was doing OCaml that I really knew of at the time. So yeah, this is my cartoon because it's about me. And it's always been about me. The first time I saw it, it was my name. So yeah, let's get on to some terminology about the OCaml module system. So it's really, OCaml as a language you can think of as 2 different layers or 2 different sub-languages within it. There's this first language which is the language of the functions and the values, and that's sort of the typical thing you'd be programming in day to day. It's kind of what you'd be programming in Haskell. And then in OCaml there's this second layer which is the language of modules and functions. And they're really 2 separate parts of the language, and they sort of interact in ways, but they are 2 separate parts. And so the parts of the module system we're going to look at is structures, signatures, and functors. But first we need a little detour and look at how OCaml does type declarations. So it's not really scary, it's just a little bit different. So basically looking at, we've got a Haskell at the top and OCaml underneath. So Haskell has got uppercase starting for the types, whereas OCaml's got lowercase. So you can see that for the ints and the bools and stuff in the list. Type variables in OCaml are written with a single quote. So you can have a look at these the definition of fold. So fold left is taken from Haskell, and this is the fold left from OCaml. And you can see where you've got sort of A's and B's in Haskell, you've got quote A's, quote B's in OCaml. So it's kind of the same, even though they're using A's and B's in a different order, which is annoying. And then the last bit is the type constructors are reversed. So where you've got, essentially you've got this list of A's, or it's probably better to look at these, you get a tree of A's in Haskell, you've got a quote A of trees. So it's just reversing them. So you can kind of look at it and work out what it's actually doing. So enough of that. Hopefully that's enough of an explanation so people can read these sorts of things. So first is structures. So structures in OCaml provide units of organization. So it's basically somewhere where you put all your types and your functions together. And we introduce them with this struct keyword and close it with an end keyword. So here we've got a type T, which we've bound to an int. We've got a set, which is a list of T's, and we've got a couple of functions there. So that's a structure. And the interesting thing with structures is if you don't define a name for them, so this is called int set, if we didn't define a name for it, it'd get the name of the structure from the file name. But it doesn't have to be, like, there's not a one-to-one mapping like there is in Haskell. It's not, the module name needs to match the file name. So calling structures, pretty straightforward. It's just using dot notation. So whatever the name of the structure is, dot, whatever it is you want to access within that. So T, empty, pretty much as you'd expect. The interesting thing about structures in OCaml is they can be nested. So nested structures within nested structures. So here we've got this int set. Within that we've got another struct which is compare, and that's got some things in there. And if we want to access those, that's dotted as well. So fairly as you'd expect. But then using structures. So we don't really want to use that long name to refer to the structure all the time. So we've got three main ways that we can make that more palatable, I suppose. The first one is we can open the structure at the top of the file. So if we open int set, it brings everything within int set into the scope of that file. So here we're just calling compare equal without actually referring to int set. The second option you've got, which I really miss in Haskell, is you've got these local opens. So you can refer to the module with the dot dot, and then within those round brackets, everything's scoped within that particular module. So you don't need to use the longer name to refer to it. And that's quite handy if you're only using that module in one sort of place within your code. You can just include it there with using a local open, and then everything's scoped within that module. And the final option you've got is you can bind it to a shorter variable name. So you just do let module s, and then you use that shorter name. So that's quite helpful as well. So that's structures. So the next thing that we don't really have in Haskell, I suppose, is interfaces. So interface is defining, well, a signature is defining an interface for a structure. And this is basically a list of declarations of types and functions, but without any implementations. And we're introducing it with the sig and end keywords. But the interesting thing about signatures in OCaml is that you can change, they don't have to match what is exported with the structure. So you can refine things, you can be more constrained about the types you export, and you can choose to not export types at all. So you can have some of your types as abstract. So anything outside of that structure can't refer to the internal representation, which is helpful. And typically when you're looking at OCaml projects in the wild, you'll have the structure in one file, so it'll be, say, set.ml in one file, and then the other file will be set.mli, and that will include the signature. But it doesn't have to be that way. You can have them both in line in the .ml file. So have a look at the example. Yeah, it's the monad example. Hopefully everyone's familiar with that. So this is just the signature and defining the interface for a monad. And these are just infix operators. So fairly simple. So now we get to the cool part, functors. So functors, when I first heard about functors in OCaml, I thought, cool, I've got fmap. But no, functors in OCaml aren't Haskell functors. They're not providing a map, like an fmap across the structure, although they are functors in the category theory sense of things. So functors in OCaml are a function from a struct to a struct. So basically you're parameterizing a struct in terms of another struct, and it produces a struct. So it is, like, category theory-wise, it's a functor, but it's not an fmap functor. So yeah, another way to think of it is you're lifting functions into the module language. So let's have a look at how that looks in OCaml. So here we're introducing a signature for some sort of ordering, and we've got a function comparing two types of t and gives us an int. So that's -1, 0, 1, depending on how they are ordered. And then we're reintroducing this set, which we had before, but instead of we've put the quote t everywhere, so it doesn't have a type for t yet. So that's just signatures. So this is where the functor comes in. So we've got this functor called makeSet, and it's parameterized over this ordering, which we've bound to O. And then everywhere that we want to rely on the ordering, we're using the O to bind things from O to things inside this functor. So we're binding the type T from the T of O, and then inside our member implementation, we're using the compare from O to do the implementation. So we're not relying on anything concrete inside the ordering. We're just relying on the interface that we're getting from ordering. And so this is an example of a functor with one argument, but you can have arbitrary arguments to functors. So you could have, and you just introduce those as another round bracket, another variable name, ... and then whatever the signature or structure for it is. Yeah, and using our functor. So we had that ordering signature before, so we want an ordering for ints. So that's what we're doing in this top bit, the int ordering. We're binding the type t to an int, and we're binding the compare to an int compare that we get from the standard library in OCaml. And then we're using that signature, or that struct there, and passing it into the makeSet functor, and that's going to give us an int set which is ordered in relation to this int ordering that we've defined. And then if we want to use it, we refer to the int set and we do our inserts or member or something, or we can use this local open syntax, which is a little bit more convenient for that. So that's how we use a functor. So just in review, structures group together types and functions with implementations, whereas the signatures are an interface for a structure, so they don't define any implementation for things. And functors are just functions from a struct to struct. So if nothing else, I'd like people to take this away with them so they understand what these things mean and how they compare to type classes, which is what we're going to get onto next. So type classes. Type classes are great, but they're a particular technique and they're not the same as a module system in OCaml. So type classes in Haskell are really about bringing implicit program construction and ad hoc polymorphism to Haskell. And by implicit program construction, I mean when you use a type class, you don't specify the instance of that type class you're using at that point. Haskell goes away and finds that type class based on the type that you're using. Whereas in modules, like OCaml modules, the emphasis is not so much about this ad hoc polymorphism. It's more about explicitly constructing programs and decomposing larger programs into smaller pieces. So it's not the ad hoc polymorphism, but there's certain things that cross over between the two. So there's things that you can do in type classes that you can do in the module system. So it's interesting to look at how these two concepts map. So I'm probably oversimplifying the motivations on both sides, and probably people won't really agree with the ad hoc polymorphism necessarily, but yeah, there's significant overlap. So let's have a look at some steps that we can use to translate type classes into signatures, so there's a direct comparison between the two things. So up the top here we've got this Haskell type class, which is show, and it provides us a function from an A to a string. So if we were to write that in OCaml, we'd introduce a signature, and so we've got a signature show, we've got a type T, and then we've got the same function. So those are sort of the equivalent things. So if you're converting Haskell into OCaml, that's the first step. So your type classes would become signatures. The next step, in Haskell, you define some sort of instance for that type class for that particular type that you want. So here we've got show, but that's already provided in GHC. But you could imagine if you're using ASON or some sort of JSON serialization, you'd have to define that yourself. So the equivalent in OCaml is you've got this structure, and then you bind your type to type T, and then you provide an implementation for show. So that's the equivalent. So instances in Haskell become structures in OCaml. So using the type class in Haskell, you don't really need to do anything special. Haskell will work out what instance of that type class you want based on the value that you provide. So it's fairly straightforward. You don't need to do anything special. Unfortunately, that's not the case in OCaml. You've got to jump through at least one extra hoop. So in OCaml, if you want to use that struct and signature we had before, we need to define our function that wants to use it. So our function toCSV needs to be parameterized over the S, the show, and then we can use it. So we've got this functor here, it's across S. We've defined some implementation for showInt, and then we need to instantiate with that functor a module X, and then we can call the toCSV. And in here it's just doing it's just doing to ints. But you could imagine if you did some implementations of showInt or for real numbers or strings or something else, you could call it in the same way. So the verdict from this. So type classes can be translated into modules. There's fairly simple steps that you can go through to do that. So which is really nice if you're reading papers, and a lot of papers are written in Haskell, so you can compile them in your head or translate them in your head to OCaml and get the equivalent thing. But what you notice when we're going through all these is that the OCaml ends up being a lot more verbose. And I suppose in a less simplistic example like JSON encoding, like decoding, encoding to JSON, the Haskell would end up being a little bit more verbose because you'd have to write that instance of the type class. But still, it's more verbose. It's kind of nasty where you have to wrap the things in functors and instantiate them with a particular version of the functor. But you can do it, and it's not too terrible considering the motivation for modules in OCaml isn't to provide that ad hoc polymorphism. It's for program construction and decomposition. But really what Haskell's doing under the hood is that it is actually tracking that mapping from a type to a type class instance. It's just that you don't have to care about it. There's sort of reasonable guarantees that there's only one instance of that type class. But yeah, if you're sufficiently devious, you can get around that if you want. But usually you don't want to. Okay, so now going on to some things that I probably shouldn't say that they aren't possible in Haskell, but they're not as pleasing, I suppose, to me anyway. So a few things that you can do in OCaml that are really a bit more difficult to do in Haskell is we can do type-safe extensions to existing modules. So say you've got a particular module you're getting from another library, and you don't quite like it or you don't agree with the implementation of a particular function. In your code, you can pull in that thing and you can overwrite that function or you can add new functions to it. The other really cool thing is parameterizing libraries over different things. So you can parameterize them over architectures or platforms or compilers or different runtimes if you want. And the common code's common, and you just use functors to parameterize over those. And the other cool thing is parameterizing libraries over their dependencies. Similar to how backpacks going to work for Cabal, you can parameterize libraries over their dependencies in OCaml. And the last one maybe not quite so compelling, but you can instantiate modules with state. So you could use a functor to instantiate a module which keeps a particular state. It doesn't need to be mutable state. It could be sort of some initialization stuff that you want to keep in there. Yeah, so let's go through some examples of each of those. So first, type-safe extensions. This is used heavily in recursing a little bit. The OCaml standard library is fairly poor. So there's a couple of replacements for the standard library that take the standard library and extend it with more useful functions. There's core and there's batteries. And they use this technique to extend the standard library. So basically what you would do is you define some sort of module. So we've got a listy module, and using the include keyword, we're bringing in everything from the list module that's in the standard library. And then we're defining, so intersperse doesn't come in the standard library, so we want that. So we're defining an implementation of intersperse. And then at the end of that, we're re-exporting our listy module and replacing the existing list module. So you could think in your program, as long as you include this at the top of your file, then it would include the intersperse, and it'd look the same as the standard library, so you wouldn't need to do anything. So it's monkey patching, but it's type safe. And the interesting thing with OCaml is you can do the same thing for signatures. It's just a different syntax. So you could include module type of list, which would include everything from the list signature into your signature, and then you could mess around with things there. Okay, parameterizing libraries. So this is a really interesting thing for me personally, because I really like the way that these libraries do this. So first example is CoHTTP, which is a library for creating HTTP daemons. And basically, there's this common set of code for it, but it's parameterized over 4 different asynchronous libraries. So you've got, first one is LWT, which is backed by Unix threads, async, which is backed by Unix threads but slightly different, and then you've got these 2 other ones. So you've got an OS independent one, which is used in the Mirage unikernel. So there's no OS underneath it, it's just raw C and whatever they provide in that. And you've also got an asynchronous one backed by JavaScript. So the same common code works across all of those, and they just, when you build it, you say which one you want to use, and it parameterizes over that, which I think is really cool. A couple of other examples is the Mirage unikernel. So applications you write are functorized across the OS components they use. So basically, I've got an example after this, but you've got a functor, which is your main function that you want to write, and you just include the different modules that you want to use. A couple of other ones, Ermine, which does the same sort of thing, but across storage implementations, and OCaml graph, which provides generic graph libraries in OCaml, but using functors that can be parameterized across different implementations or instances. But I suppose to do the same sort of thing in Haskell, you have to use things like CPP to sort of work around or detect when things are there. And it's not, basically with CPP, it's pretty portable, but it's untyped, and it's got a different syntax to Haskell, and it's just not really that nice. It's kind of gross. Ideally, you'd want these things to be typed. You know, it's like you're writing C code in your Haskell. So this is an example of the Mirage OS. So they define these signatures for particular devices, and then here we're defining a console device, and we're bringing in the signature for int, and we're binding the error to our error type that we've defined here, and we're introducing this log s. So log a string of something to string and tagging it with some sort of IO here. And so our main function that would actually use those 2 things is a functor. So we've got a functor across some sort of console, and we're providing the implementation, and we're referencing C, and our implementation doesn't look inside C to see how it works. It's just using that interface. So that's how you define write programs in Mirage. And as I said, you can go across multiple things, so your functor doesn't have to be across one particular thing. So this is an example where they're going across a console, a file system, I'm not sure what TMPL is, and some sort of HTTP server. So you can parameterize across multiple things. Obviously, as you get more and more things you're parameterizing across, it gets more complicated, and you've got more dependencies, but you can do it. Another example from the core library is this monad thing. So basically, they've defined a basic interface for a monad. So you've got a bind and return. You've got this type S. Don't worry about that too much. It's a signature that brings together the basic type and a bunch of convenience and infix operators. And then you've got this functor make, where if you pass in something that conforms to basic, it'll provide you all those derived implementations of functions from that. So as long as it conforms to this basic signature, then you can make a functor out of it. A monad out of it, and you can use the sort of bind syntax and all those sorts of things, which is kind of cool. So I mentioned earlier that modules aren't for ad hoc polymorphism, which is true. There's a proposal that's coming in OCaml called Modular implicits, which is explicitly for improving the support for ad hoc polymorphism in OCaml. And it's not quite fully baked, and it's not merged into the main OCaml compiler yet, but you can try out a branch of it, and this is what it looks like. It's taking inspiration from Scala's implicits, but it's it's a little bit safer perhaps than Scala implicits. So again, we'd have this signature show, which you can think of as our type class. We're defining a function that goes across show. You'll note here that it doesn't have to be a functor necessarily, although it sort of looks like a functor because you've got this implicit S, which you're binding to show, but it's not necessarily a functor. And then you've got this implicit, which you can think of as an instance of a type class here. And so we're providing an implementation of showing an int here, and we're just printing it out. And then when we want to use it, we don't have to instantiate, we don't have to pass this implementation into a functor and call it to go to module out, then call it on the module. We can just call it straight away. The nice thing with this is if you've got conflicting instances here, like of these implicits, you'll get a compile time error. So it won't try and, so there's no way that it works out this one takes precedence over this one. It will just give you an error and it won't compile. But it still keeps in that, I suppose that OCaml's philosophy of being more explicit about how you construct your namespace. So you need to explicitly construct the namespace. It's not implicit for you. So this is all good. It's like, OCaml's fantastic. We can do all these things. But we might want to do that in Haskell. So one way that we can do that in Haskell is we can use this technique using records as modules. So basically, this is sort of a cut down version from some Ambiata code. So basically, we've got this record, and it's got two slots in there, and they correspond to two functions. So we've got some sort of record something in a database or some data store, and look up something. Don't worry too much about the type signatures because they probably don't make a lot of sense, but you've basically got two slots where you can put two different functions in. And then somewhere else now in our code, we've got somewhere where we want to talk to S3 for this. So we create an instance of index, and we put in the functions that we know that work for S3. And then when we, and this is sort of part of a record instance, record function that we've defined. So this is nice. You can kind of do a reasonable number of things that you can do with modules in Haskell. You need to be careful that you don't export how to create these index data types too widely. You want to make sure that your record and your lookup match what will work for that particular data store. But it's quite good, and we've used it in quite a few places. The downsides of it is you do have the record syntax, so you've got to make sure that your keys are unique. It's a little bit clunky when you've got to do that. There's probably a slight performance hit that you'll take on this because you're doing double dispatch everywhere. The compiler doesn't necessarily know that this is how you're using this. It's not a type class or something. It can't know at compile time necessarily that you want to go through there. So you have a bit of double dispatch. And as I said, you want to be careful on how you can construct these index things. But it's a useful technique. So in summary, I think that OCaml modules are worth knowing about, even if you don't really use them. I know I've heard that before about a lot of things, but it's interesting to have a different point in the design space to compare to type classes, and especially when people are starting to talk about wanting a module system in Haskell and what that means. A lot of people refer to the ML module system, and it's good to know what they're actually referring to. So in summary, structures combine types and functions with implementations. Signatures combine types and functions without implementations. And functors in OCaml are just functions from structs to structs. They're parameterized structs. And there's a really simple translation you can do from type classes to modules. So you can read a paper in Haskell and see all the Haskell code, and if you want to, you can go through and translate that directly to OCaml, which I tend to do quite a lot. So that's about all I've got. I think I was pretty fast with that. Yep, that's me. I'm at Ambiata, yet another Ambiata person talking at everyone. And these are a few links for sort of interesting papers on the module system, how you can use the module system in ML, and how they're using it, say, in Mirage OS or the graph library. Or there's this proposal here, which is at ICFP this year, which is about sort of unifying the type level and the module level in ML with another version of ML, and some links to some of the code that I was talking about. Thanks.